Scientists just detected something with the James Webb Telescope that has no business existing in our universe. A massive pattern in how ancient galaxies rotate that directly violates the laws of cosmic randomness. And the only theory that explains it is so disturbing that researchers are genuinely debating whether everything we've ever observed is actually happening inside the event horizon of a black hole. We can't see because we're trapped on the inside looking out. And if you want to know everything about this discovery, then watch this video till the end and subscribe to the channel. Let's begin. According to our standard cosmological models, galaxies should form with random orientations, their rotation determined by local conditions, by the turbulence of gas clouds collapsing under their own gravity, by chance encounters and mergers with neighboring structures. In a universe that is fundamentally isotropic, meaning the same in all directions, and homogeneous, meaning the same at all locations, there should be no preferred direction for galactic rotation. Some galaxies should spin clockwise relative to our viewpoint, others counterclockwise, the distribution entirely random. A cosmic coin toss repeated trillions of times across the observable universe. Yet what JWST revealed was anything but random. A significant proportion of these ancient galaxies, approximately 60% according to initial analysis, showed a preference for rotating in the same direction. This was not a subtle effect buried in statistical noise, not something that might emerge from squinting at ambiguous data. It was a clear pattern, a large-scale coherence in the cosmos that should not exist according to our current understanding of how the universe works. To appreciate why this discovery is so troubling, we need to understand what we expected to see and why. Galaxies are vast collections of skis, gas, dust, and dark matter bound together by gravity, typically containing hundreds of billions of stars arranged in distinctive shapes. Some galaxies are spirals like our own Milky Way, with graceful arms curving outward from a central bulge. Others are elliptical, shaped like cosmic footballs with stars distributed more uniformly. Still others are irregular, lacking any clear structure at all. Each galaxy rotates, sometimes slowly over hundreds of millions of years, sometimes more rapidly. This rotation a consequence of the angular momentum present in the gas clouds from which they formed. When a cloud of gas begins to collapse under its own gravity, any initial rotation, however slight, becomes amplified as the cloud contracts. The same physics that causes a figure skater to spin faster when pulling in their arms. The direction of that initial rotation depends on countless factors: turbulence in the primordial gas, gravitational tugs from nearby structures, shock waves from distant supernova, the complex interplay of forces present in the early universe. With so many random influences, cosmologists have always assumed that the resulting galaxy spins would show no overall pattern, no cosmic preference for one direction over another. This assumption is built into the very foundation of modern cosmology, into what we call the cosmological principle. This principle states that on the largest scales, the universe is both isotropic and homogeneous. Isotropic means that, no matter which direction you look, the universe appears statistically the same. There is no cosmic north or south, no preferred axis, around which everything aligns. Homogeneous means that no matter where you are in the universe, your local region looks statistically similar to any other region. You are not at any special location. There is no center, no edge, no place that is fundamentally different from anywhere else. These assumptions have been tested extensively and appear to hold remarkably well when we look at the distribution of galaxies across vast distances, when we measure the cosmic microwave background radiation that fills all of space. when we study the large-scale structure of the universe. The cosmological principle has been one of the most successful and fundamental assumptions in all of physics, allowing us to build coherent models of cosmic evolution that explain everything from the abundance of light elements to the acceleration of cosmic expansion. Yet now, we face an observation that seems to violate this principle. If approximately 60% of early galaxies preferentially rotate in one direction, then the universe is not isotropic. There is a preferred direction, a cosmic axis, a handedness to the universe that should not exist. The implications cascade outward like ripples from a stone thrown into still water. If this observation holds up to scrutiny, if it survives further analysis and independent confirmation, then something is fundamentally wrong with our cosmological models. Either the early universe was not as uniform as we thought, or some large-scale force or structure influenced galaxy formation in ways we have never considered, or our observations are taking place within some larger context that imposes order on what we assumed was random. This is where the black hole hypothesis enters the picture, offered not as a certainty, but as a possibility too intriguing to ignore. The suggestion is this: what if the universe we inhabit, everything we can observe with our most powerful instruments, everything that has ever been or will ever be accessible to human investigation, exists inside a massive black hole? Not inside, in the conventional sense of having fallen through an event horizon and now tumbling toward a central singularity, but rather constituting a universe-sized black hole structure where the geometry of space-time itself has been fundamentally altered by the gravitational collapse that created it. In this scenario, the apparent alignment of galactic rotations would be a consequence of the topological and gravitational constraints imposed by existing within such a structure, a kind of cosmic fingerprint revealing the true nature of our reality. Before we can evaluate whether such an idea makes any sense, we need to understand what black holes are and what it means to be inside one. A black hole forms when matter becomes so densely compressed that its gravitational field becomes strong enough to prevent even light from escaping. The exact process depends on the mass involved. For stellar mass black holes, those with masses between a few and a few hundred times that of our Sun, the trigger is the death of a massive star. When such a star exhausts its nuclear fuel, it can no longer generate the outward pressure needed to resist its own gravity. The core collapses catastrophically in a fraction of a second, and if the remaining mass is sufficient, nothing can stop the collapse. The matter compresses into a region of space so small and so dense that it creates a boundary called an event horizon, a surface of no return beyond which the escape velocity exceeds the speed of light. Anything that crosses the event horizon, whether matter, light, or information, can never escape back to the outside universe. The horizon marks a fundamental boundary in space-time, a point of no return imposed by the structure of space and time themselves. Inside the event horizon, our conventional understanding of physics becomes uncertain. According to general relativity, Einstein's theory of gravity that describes how mass and energy curve spacetime, the interior of a black hole is a region where spacetime curvature becomes extreme. At the very center lies what we call a singularity, a point where density becomes infinite and our mathematical equations break down completely. We do not actually know what happens at a singularity because general relativity predicts its own failure there, suggesting that a more complete theory, perhaps one that unifies gravity with quantum mechanics, is needed to describe the true nature of that region. But we do know some things about the space between the event horizon and the central singularity. time and space exchange their properties in a sense. Outside a black hole, you can move freely through space, but are dragged inexorably forward through time. Inside a black hole, all paths through spacetime lead toward the singularity just as surely as all moments outside led toward the future. The singularity becomes your inevitable future, a destination you cannot avoid no matter what you do. This interior region, the volume enclosed by the event horizon, is in some sense an entire universe unto itself, causally disconnected from the exterior. Nothing that happens inside can influence anything outside. And from the perspective of an external observer, an object falling into a black hole appears to slow down, redshift, and fade away, forever frozen at the event horizon, taking an infinite amount of time to actually cross. But from the perspective of the infalling object, nothing special happens at the horizon. It crosses through in finite time, continues inward, and eventually meets whatever fate awaits at the singularity. This divergence of perspectives, the fact that different observers can have fundamentally different experiences of the same events, is one of the most profound and counterintuitive features of relativistic physics. Now consider a different kind of black hole, not one formed from a collapsed star, but one with the mass of billions or trillions of suns, or even more. Such supermassive black holes exist at the centers of most galaxies, including our own Milky Way, objects with masses measured in millions or billions of solar masses. The Schwarzschild radius, the size of the event horizon for a non-rotating black hole, grows proportionally with mass. For a solar mass black hole, the horizon has a radius of about 3 kilometers. For a supermassive black hole with a billion solar masses, the horizon radius is about 3 billion kilometers, roughly 20 times the distance from the Sun to Earth. As black holes grow larger, the density required to create them actually decreases. The average density inside the event horizon of a supermassive black hole can be lower than the density of water, or even air, because the volume enclosed grows with the cube of the radius, while the mass grows linearly. For a truly enormous black hole, one with the mass of the observable universe, roughly 10 to the 53rd kilograms, the event horizon radius would be comparable to the size of the observable universe itself, some 46 billion light-years. This mathematical coincidence has not gone unnoticed. Several physicists over the years have wondered whether our universe might be the interior of such a structure. The idea is not that we fell into a pre-existing black hole from some external universe, but rather that the Big Bang itself might represent the formation of a black hole as seen from the inside, that the expansion we measure might be the growth of the interior volume as matter and energy spread out within the horizon. In this view, the universe is not a black hole that formed from collapse, but a black hole that formed from a kind of quantum tunneling or fluctuation, creating a causally disconnected region of space-time that we experience as the entirety of reality. The boundary of this region, if it exists at all in a form we could identify, would be beyond our cosmic horizon, forever unreachable as space continues to expand. But how would such a structure explain the alignment of galaxy rotations? The key lies in the geometry and topology of space-time within a black hole. In the standard picture of cosmic expansion, space is not expanding into anything. There is no external arena or pre-existing void into which the universe grows. Rather, the distances between objects increase because space-time itself is expanding, stretching like the surface of an inflating balloon. This expansion is described by a metric, a mathematical object that tells us how to measure distances and time intervals in curved spacetime. The most commonly used metric for cosmology is the Friedmann-Lemaitre-Robertson-Walker metric, which assumes perfect homogeneity and isotropy. But inside a black hole, different metrics apply, and the structure of spacetime can impose constraints that break this symmetry. One possibility is that the universe as we know it exists in a rotating black hole, rather than a simple static one. In general relativity, black holes can have mass, electric charge, and angular momentum. A rotating black hole, described by the Kerr metric, has a more complex structure than a non-rotating one. The rotation drags spacetime around with it, an effect called frame dragging, in which objects near the black hole are forced to rotate in the same direction as the black hole itself, regardless of their own initial motion. Near a rotating black hole, spacetime itself is swirling, and any object embedded in that spacetime will be carried along with the flow. If our universe exists within the interior of a rotating black hole structure, then this frame-dragging effect could manifest on cosmic scales, influencing the formation and orientation of galaxies. Galaxies forming from collapsing gas clouds would naturally acquire angular momentum aligned with the rotation of the surrounding spacetime, producing the observed pattern of preferential rotation direction. Another possibility relates to topology. Topology concerns the overall shape and connectivity of space, properties that remain unchanged under continuous deformation. A sphere and an ellipsoid have the same topology, even though their geometries differ. A coffee cup and a donut have the same topology because each has a single hole, and one can be continuously deformed into the other. The topology of the universe is one of the great open questions in cosmology. Is space infinite in all directions, or does it close back on itself? If you traveled far enough in one direction, would you eventually return to your starting point from the opposite direction? Our measurements of the cosmic microwave background suggest that the universe is very close to spatially flat on large scales, but they do not definitively rule out subtle curvature or non-trivial topology. If the universe has a particular topological structure, perhaps one imposed by being the interior of a black hole, this could create preferred directions or axes that influence the formation of structures. Certain topological configurations could produce correlations in galaxy orientations across vast distances, patterns that would be invisible in the local properties of spacetime, but would emerge when we observe the universe on its largest scales. There is also the question of how information and structure are preserved or destroyed in black holes. The black hole information paradox, a long-standing puzzle in theoretical physics, concerns the fate of information about matter that falls into a black hole. According to classical general relativity, information is lost forever behind the event horizon. But according to quantum mechanics, information cannot be destroyed. This tension has led to decades of debate and numerous proposed resolutions, some involving the idea that information is somehow encoded on the event horizon itself, on a two-dimensional surface that bounds the three-dimensional interior. If our universe is a black hole, then perhaps the fundamental information about our reality is encoded on a distant boundary, and what we perceive as three-dimensional space with structure and complexity is actually a projection or hologram of that boundary information. In such a scenario, correlations and patterns in the universe might reflect the underlying structure of the boundary encoding, producing phenomena like the alignment of galaxy rotations that seem inexplicable from our interior perspective. Before we become too committed to the black hole hypothesis, we must carefully consider more conventional explanations for the observed pattern. Science progresses by testing predictions against observations, And when an observation conflicts with theory, the first step is not to overturn the theory, but to examine whether the observation might be explained by more prosaic causes. Observational bias is always a concern in astronomy. When we observe distant galaxies, we measure their rotation by examining the Doppler shift of light from different parts of the galaxy. Light from the side of the galaxy rotating toward us is shifted toward shorter, bluer wavelengths, while light from the side rotating away is shifted toward longer, redder wavelengths. By mapping these velocity differences across the galaxy, we can determine both the rotation speed and the direction of rotation relative to our line of sight. However, this measurement depends critically on our viewing angle. If we observe a galaxy edge-on, the rotation is very apparent. If we observe it face-on, the rotation is much harder to detect. The sample of galaxies for which we can reliably measure rotation is therefore biased towards certain orientations, and it is conceivable that this bias could produce an apparent pattern in rotation directions, even if no true pattern exists. Selection effects are another concern. The galaxies in the JWST sample are not randomly selected from all possible galaxies in the early universe. They are the galaxies that happen to be bright enough and well resolved enough for us to measure their rotation accurately. These galaxies might be systematically different from the broader population in ways that affect their rotation properties. Perhaps they formed preferentially in particular environments, or at particular times, or with particular masses, and these factors somehow correlate with rotation direction. Determining whether the observed pattern is real or an artifact of selection requires careful statistical analysis and, ideally, observation of additional samples using different selection criteria and different instruments. Instrument calibration is always a potential source of systematic error. The JWST is an extraordinarily sophisticated instrument, but it is not perfect. Its detectors, optics, and pointing systems all have subtle biases and imperfections that must be carefully calibrated out of the data. If there is any systematic error in how the telescope measures velocities or positions, or if there is any subtle drift or wobble in its pointing, these effects could conceivably produce an apparent asymmetry in measured galaxy rotations. The JWST science teams work diligently to identify and correct such effects, but the possibility can never be entirely eliminated, especially when dealing with faint, distant objects at the limits of the telescope's capabilities. There is also the possibility of unknown local influences on galaxy formation. Perhaps the region of the universe we are observing, distant though it may be, was subject to some large-scale flow or turbulence in the early universe that produced correlated rotation directions. Cosmologists know that the universe was not perfectly smooth in its earliest moments. Quantum fluctuations during the inflationary epoch, the brief period of exponential expansion thought to have occurred in the first fraction of a second after the Big Bang, created tiny density variations that later grew into galaxies and galaxy clusters. Perhaps these fluctuations also produced velocity flows, streams of matter moving coherently across vast regions, and galaxies forming in these flows naturally acquired rotation aligned with the flow direction. Such an effect would not violate the cosmological principle on the very largest scales, but could produce patterns on intermediate scales, patterns that would be visible in surveys of particular cosmic volumes, but would average out when looking at the universe as a whole. To evaluate these alternative explanations and to test the black hole hypothesis, we need to examine how well they fit within our current understanding of cosmic structure and evolution. The standard model of cosmology, sometimes called the lambda CDM model, has been remarkably successful at explaining a wide range of observations using a relatively small number of parameters. According to this model, the universe began in a hot, dense state roughly 13.8 billion years ago and has been expanding and cooling ever since. The expansion is not a movement of galaxies through space, but an increase in the distances between them as space itself expands. This expansion is governed by the energy content of the universe, which consists of roughly 5% ordinary matter, the atoms and molecules that make up stars and planets and us, 27% dark matter, a mysterious substance that interacts through gravity but not through light, and 68% dark energy, an even more mysterious component that causes the expansion of the universe to accelerate. The cosmic microwave background, radiation left over from when the universe became transparent about 380,000 years after the Big Bang, provides our best evidence for the validity of this model. The CMB has been measured with extraordinary precision by satellites like WMAP and Planck, revealing a nearly uniform glow of microwave radiation coming from all directions in the sky. The temperature of this radiation is almost exactly the same in every direction, varying by only about 1 part in 100,000. These tiny temperature fluctuations correspond to density variations in the early universe, the seeds from which galaxies and galaxy clusters later grew. The statistical properties of these fluctuations match the predictions of the lambda-CDM model extremely well, strongly supporting the idea that the universe is homogeneous and isotropic on large scales. Yet the CMB does show some anomalies that have puzzled cosmologists for years. There is an apparent asymmetry in the power spectrum, with fluctuations appearing slightly stronger on one side of the sky than the other. There is a mysterious cold spot, a region significantly colder than average, whose origin remains debated. There are hints of alignments in the multipole moments of the CMB, patterns that some researchers have called the axis of evil, a tongue-in-cheek reference to the unexpected structure they reveal. Most cosmologists believe these features are statistical flukes or consequences of foreground contamination, signals from our own galaxy or the local universe that have not been perfectly subtracted from the data. But a minority has wondered whether they might be real features of the universe, hints that the cosmological principle is not exactly true, that the universe has subtle large-scale structures or preferred directions that our models do not account for. The alignment of galaxy rotations, if confirmed, would add to this list of anomalies and would demand a serious rethinking of cosmic structure. If galaxies preferentially rotate in one direction, then some large-scale field or structure must have influenced their formation. In conventional physics, the most obvious candidates would be magnetic fields or angular momentum. Large-scale magnetic fields do exist in the universe, generated by various astrophysical processes and potentially amplified during galaxy formation. If a coherent magnetic field pervaded the early universe, it could have influenced the collapse of gas clouds and the rotation of the resulting galaxies. Similarly, if the universe as a whole possessed some net angular momentum, perhaps imparted during the Big Bang or inflation, this could manifest as a preferred direction for galactic rotation. However, there is no evidence for such large-scale fields or rotation in current cosmological models, and introducing them would require explaining where they came from and why we do not observe their effects in other contexts. This brings us back to the black hole hypothesis, which offers a potential framework for understanding these anomalies without invoking entirely new physics. If the universe is the interior of a black hole, then the observed properties of cosmic structure might simply reflect the geometry and dynamics of that black hole. The alignment of galaxy rotations could be a consequence of frame dragging in a rotating black hole. The anomalies in the CMB could reflect the topology or boundary conditions imposed by the black hole horizon. The expansion of the universe could be understood as the evolution of the black hole interior, described by equations that differ subtly from the standard Friedmann equations used in conventional cosmology. One of the most intriguing aspects of this hypothesis concerns the nature of time and expansion within a black hole universe. In the standard cosmological model, the Big Bang represents the beginning of time, a boundary or singularity beyond which our physics cannot describe anything. Asking what happened before the Big Bang is often considered meaningless, like asking what lies north of the North Pole, because time itself began with the Big Bang. But in the black hole interior model, the situation might be different. The Big Bang could represent not the beginning of time, but the formation event of the black hole, as seen from inside. There could be an outside, a larger universe in which this black hole exists, but that outside would be forever inaccessible to us, separated by an impassable event horizon. Time inside a black hole still flows forward for observers within, but the nature of that flow is altered by the extreme curvature of spacetime. The expansion of the universe takes on a different character in this picture. Rather than space expanding into nothingness, it might be more accurate to say that the black hole interior is evolving, its internal volume growing according to the dynamics of black hole physics. General relativity tells us that the interior of a black hole is not a static region, but a dynamic one, with spacetime itself falling toward the central singularity. For an external observer, the black hole is a stable object that can persist for enormous lengths of time. But from the interior perspective, the situation is more complex. The interior spacetime has a definite structure that evolves over time, and the volume available to objects within that interior changes according to specific equations. In certain models, the expanding universe we observe could be the interior of a black hole, still in the process of forming from collapse. Imagine a massive region of matter in some parent universe beginning to collapse under its own gravity. As viewed from outside, this collapse appears to slow down and halt as the matter approaches the event horizon, taking an infinite amount of time to complete. But from the perspective of observers forming within the collapsing region, the collapse happens in finite time, and the interior volume continues to grow and evolve. This interior becomes a causally disconnected region, a universe unto itself, and observers within it might measure an expansion that resembles what we observe in our own universe. The expansion rate, the density of matter and energy, the formation of structures, all would be determined by the initial conditions of the collapse and the physics of black hole interiors. Such a scenario has profound implications for the ultimate fate of the universe. In conventional cosmology, we can project the future evolution of the universe based on its current expansion rate and energy content. If dark energy continues to dominate, the universe will expand forever, accelerating, becoming ever colder and more dilute in a state sometimes called the Big Freeze or heat death. Eventually, after incomprehensible spans of time, even black holes will evaporate due to Hawking radiation, leaving only a thin soup of particles and radiation in an ever-expanding void. But if the universe is inside a black hole, this fate might be forestalled or altered. The evolution of the interior is constrained by the overall structure of the black hole. There might be a maximum size or age beyond which the interior cannot grow, or the expansion might eventually reverse into a contraction as the interior approaches the central singularity. the end state could be very different from what conventional models predict. Perhaps a collapse back to high density rather than an eternal expansion to emptiness. The black hole universe hypothesis also intersects with ideas about the multiverse, the possibility that our universe is just one of many causally disconnected regions of space and time. In some multiverse theories, particularly those arising from eternal inflation, the universe we observe is just one bubble in an infinite sea of bubbles, each with its own properties, its own laws of physics, its own history. If black hole interiors can serve as universes, then every black hole in our universe might contain another universe, and our universe might itself be inside a black hole that exists in yet another parent universe. This creates a nested hierarchy of universes, a cosmic fractal where each level contains black holes that spawn new levels, extending infinitely in both directions. While this might sound like pure fantasy, it emerges naturally from the combination of general relativity and quantum mechanics, and several respected physicists have explored the idea seriously. The JWST observations that sparked this discussion are just the beginning of what will be a long process of investigation and debate. The telescope is expected to operate for at least another decade, and it will continue to observe distant galaxies, measuring their properties in ever greater detail. Astronomers will expand the sample of galaxies with measured rotations, determining whether the apparent alignment holds up as more data are collected. They will analyze different populations of galaxies from different cosmic epochs and different environments, searching for variations in the pattern that might point to an underlying cause. They will cross-check the measurements using different instruments and techniques, ensuring that the observed effect is not an artifact of the specific methods used by the initial study. Other telescopes will contribute to this effort as well. Ground-based observatories equipped with adaptive optics can achieve remarkable resolution, sufficient to measure the rotation of relatively nearby galaxies with high precision. Radio telescopes can detect the emission from neutral hydrogen gas in galaxies, providing an independent measure of rotation that does not rely on visible light. Future space missions, perhaps including even more powerful telescopes than JWST, will push observations to even earlier cosmic times, to the very first generation of galaxies forming in the universe. Each of these observations will help to constrain the pattern, to determine whether it is real. If so, what it means. Testing the black hole hypothesis directly is more challenging because it makes predictions that are difficult to distinguish from conventional cosmology. If the universe is inside a black hole, what specific, testable predictions does that make? One possibility concerns gravitational lensing, the bending of light by gravity. Light traveling through curved spacetime follows curved paths, and if the curvature is strong enough, multiple images of a distant object can appear, or the object's appearance can be distorted into arcs or rings. We observe gravitational lensing throughout the universe, caused by galaxies, galaxy clusters, and even individual stars. But the overall curvature of the universe, the large-scale geometry of space-time itself, also affects how light propagates. In a black hole universe, the global curvature might produce subtle lensing effects that would show up in statistical analyses of galaxy shapes and positions. Detecting such effects would require enormous datasets and sophisticated analysis techniques, but they might eventually be within reach. Another avenue of investigation concerns the topology of the universe. If space is finite and closes back on itself, we might be able to detect this by looking for repeating patterns in the distribution of galaxies. Imagine living on the surface of a sphere. If you traveled far enough in one direction, you would eventually come back to where you started from the opposite direction. Similarly, If the universe has a particular closed topology, light traveling far enough could potentially wrap around and produce multiple images of the same structures. Cosmologists have searched for such patterns in galaxy surveys and in the cosmic microwave background without finding any clear evidence, suggesting that if the universe is closed, it is at least much larger than the observable universe. But as our surveys improve, we might eventually detect topology if it exists. Yet even as we pursue these observational tests, we must acknowledge the limitations of science and the importance of maintaining appropriate skepticism. The history of science is filled with anomalies that appeared significant at first, but later turned out to be measurement errors or statistical flukes. It is also filled with anomalies that were real, but explained by mundane causes rather than revolutionary new theories. The scientific method demands that we approach extraordinary claims with extraordinary skepticism, that we subject them to rigorous testing, that we consider the full range of possible explanations before jumping to radical conclusions. The peer review process, in which scientific results are evaluated by independent experts before publication, serves as a crucial filter, catching errors and overinterpretations and ensuring that the literature maintains high standards. Even after publication, results are subject to replication and further testing by other research groups using independent methods and data. In the case of the galaxy rotation alignment, the scientific community is currently in the early stages of this process. The initial observation has been reported, but it has not yet been independently confirmed by other teams using different data. The statistical significance of the pattern is still being debated, with some researchers arguing it is strong enough to be taken seriously and others urging caution until more data are available. Alternative explanations are being explored and tested against the observations. This is exactly how science should work, with open debate, critical examination of evidence, and a willingness to revise or abandon hypotheses as new information emerges. The black hole hypothesis, in particular, faces significant challenges. While it is mathematically possible to construct cosmological models based on black hole interiors, making these models consistent with all of our observations is not straightforward. The cosmic microwave background, the abundances of light elements produced in the Big Bang, the large-scale distribution of galaxies, the acceleration of cosmic expansion, all of these phenomena are explained remarkably well by the standard lambda CDM model. Any alternative model, including a black hole universe, must explain all of these observations at least as well as the standard model does. Currently, no fully developed black hole cosmology meets this standard. The hypothesis remains more of a suggestive possibility than a detailed, testable theory. Despite these scientific and technical challenges, there is something deeply compelling about the idea from a philosophical and human perspective. The question of what the universe is, where it came from, and how it fits into a larger reality has captivated human imagination for millennia. Ancient cultures developed cosmologies that placed the Earth at the center of a small, bounded cosmos, with the heavens above and the underworld below. The scientific revolution displaced these geocentric models, revealing that Earth is a planet orbiting the Sun. The Sun is a star among billions in our galaxy. Our galaxy is one of billions in the observable universe. Each step in this progression has diminished our cosmic significance, removing us from any special location or status. We are not at the center, not the focus of creation, just one small part of an incomprehensibly vast cosmos that was here long before us and will continue long after we are gone. The black hole hypothesis, if true, would represent another step in this progression, perhaps the ultimate step. Not only are we not at the center of the universe, but the universe itself might be a kind of prison or container, a region of space-time enclosed by an event horizon beyond which we can never venture. Everything we can ever observe, every galaxy we can see, every star we can study, every possible destination for future space travelers, all of it would be contained within this cosmic boundary. There would be no way out, no possibility of accessing whatever larger reality might exist beyond the horizon. We would be, in a very real sense, trapped inside a black hole, and our entire history, from the Big Bang to the eventual end of the universe, would play out within that confinement. Yet, there is also something strangely comforting about this idea. If we are inside a black hole, then we are part of something larger, embedded in a structure that connects us to a parent universe. Our existence would not be an isolated cosmic accident, but part of a broader pattern, perhaps one that repeats across many levels of reality. Every black hole we observe in our universe might contain its own interior universe, with galaxies and stars, and perhaps even life. And we would be living in the interior of a black hole, observed by beings in some outer universe. The hierarchy could extend indefinitely, with universes nested within universes, each level as real and significant as any other. To make these abstract ideas more concrete, consider a thought experiment. Imagine you are an astronaut falling into a supermassive black hole, one with a mass of billions of suns. Contrary to popular depictions, you would not be immediately torn apart by tidal forces. For a sufficiently large black hole, the tidal forces at the event horizon are actually quite gentle, and you could cross the horizon without even noticing anything special at that moment. The light from the outside universe would appear increasingly blue-shifted ahead of you and red-shifted behind you as you fall. But otherwise, your immediate surroundings would seem normal. Only later, as you continued to fall inward, would the tidal forces grow strong enough to become dangerous, eventually reaching the point where the difference in gravitational pull between your head and your feet becomes lethal. A process gruesomely named spaghettification. Now, imagine that instead of a single astronaut, an entire civilization existed within the black hole, formed from matter that had fallen in long ago and settled into orbits or structures within the interior. This civilization would observe its surroundings and attempt to understand the cosmos just as we do. What would they see? They would observe matter and energy distributed around them, structures bound by gravity, light propagating through space. If the black hole were large enough and the interior geometry appropriate, they might even observe what appears to be an expanding universe, with distant structures receding as space within the interior grew. They might develop cosmological models to explain their observations. Never. Suspecting that they were inside a black hole because the horizon would be far beyond anything they could observe, and the global curvature of their spacetime would appear flat on the scales they could measure. This is essentially the situation we might be in if the black hole hypothesis is correct. We are the civilization within the interior, observing an expanding universe and developing cosmological models, unaware that everything we see is enclosed within an event horizon that bounds our reality. The alignment of galaxy rotations might be our first clue, a subtle anomaly that hints at the true structure of our cosmos. But confirming this would require observations and insights that may be far beyond our current capabilities. Another thought experiment involves considering the view from outside such a universe. Imagine an observer in the parent universe looking at a black hole that contains an entire interior universe. From the outside, the black hole is a compact object, perhaps with a diameter of tens or hundreds of billions of kilometers, not much larger than our solar system. Time for the interior civilization passes much more quickly than time for the external observer due to gravitational time dilation. Billions of years might pass inside the black hole for every single year that passes outside. The observer outside sees the black hole as a static object, perhaps accreting matter from its surroundings, slowly growing over time, but otherwise unchanging. They have no way to observe or communicate with the interior universe. The event horizon blocks all signals, all information, all causal connection. For all practical purposes, the interior universe does not exist from the outside perspective, and the outside universe does not exist from the interior perspective. Each is real, each is complete in itself, but they are forever separated by the black hole boundary. This raises profound questions about the nature of reality and existence. If entire universes can exist in regions of space-time that are completely inaccessible and unobservable from our vantage point, what does this mean for our definitions of what is real? Traditionally, science deals with the observable, with phenomena that can be measured, tested, and verified through experiment and observation. But modern physics increasingly points toward aspects of reality that may be fundamentally unobservable in principle, not just difficult to observe in practice. The interior of a black hole, the region beyond our cosmic horizon, other branches of the quantum wave, function in many worlds' interpretations of quantum mechanics. All of these represent parts of reality that might exist but remain forever beyond our ability to verify directly. This tension between the observable and the real becomes even more acute when we consider the possibility that our own universe might have this character, that we might be the unobservable interior that exists beyond someone else's horizon. It forces us to confront the limits of empiricism, the philosophy that knowledge comes from sensory experience and observation. If there are aspects of reality that cannot possibly be observed, can we still have knowledge about them? Can theoretical reasoning alone, guided by mathematical consistency and logical coherence, tell us truths about regions of space-time we can never access? These are not merely abstract philosophical questions, but practical issues that working physicists must grapple with as they develop theories about the ultimate nature of the cosmos. The black hole hypothesis also carries implications for how we understand the initial conditions and fundamental parameters of our universe. One of the great puzzles in cosmology is why the universe has the particular properties it does. Why is the density of matter close to the critical density that separates eternal expansion from eventual recollapse? Why is the cosmological constant, which drives the acceleration of expansion, so incredibly small compared to theoretical predictions, yet not exactly zero? Why do the fundamental forces have the strengths they do? And why do particles have the masses we observe? These parameters appear to be finely tuned, set to values that allow for the existence of stars, planets, and life. Change any of them by more than a small amount, and the universe would be radically different, perhaps lifeless and barren. In the standard cosmological model, these parameters are simply initial conditions, inputs to our theories that must be determined by observation because we have no deeper principle to derive them from. But if the universe is the interior of a black hole, perhaps these parameters are not arbitrary, but are determined by the properties of the black hole itself and the parent universe in which it formed. The mass of the black hole, its angular momentum, its charge, if any, these would set the boundary conditions for the interior universe. The physics of the parent universe, whatever laws and constants govern that realm, would influence the interior through the formation process. In this view, our universe's parameters reflect its origins as a black hole interior, and the apparent fine-tuning might simply reflect selection effects. We exist in an interior universe whose parameters allow for complexity and life, because only such universes can produce observers to wonder about these questions. This reasoning connects to the anthropic principle, the idea that we should not be surprised to find ourselves in a universe compatible with our existence, because we could not exist in a universe that was not so compatible. The anthropic principle is controversial in physics, because it appears to abandon the search for deeper explanations, suggesting that some features of the universe are simply brute facts that we must accept because they are necessary for our existence. But in the context of a multiverse, whether a black hole multiverse or some other variety, the anthropic principle becomes more powerful. If there are many universes with different properties, then the fact that we observe one with life-compatible parameters is not mysterious at all. It is simply a selection effect. We observe this universe because we exist in it, and we exist in it because its parameters allow for our existence. The philosophical implications extend even further when we consider consciousness and experience within such a framework. If the universe is inside a black hole, does that change anything about our subjective experience of reality? Does it matter to your daily life, to your relationships, to your sense of meaning and purpose, whether the cosmos you inhabit is a conventional expanding universe or a black hole interior? In one sense, the answer is clearly no. The immediate experience of life would be identical in either case. You would still wake up in the morning, still feel joy and sorrow, still face the same practical challenges and opportunities. The structure of matter, the chemistry of life, the biology of consciousness, all would be exactly the same regardless of the global structure of space-time. Yet, in another sense, such knowledge might profoundly affect how we think about our place in the cosmos and the meaning we find in existence. Discovering that we are inside a black hole would definitively answer the question of whether we are alone in the sense of being the only level of reality. There would be a larger universe out there, even if we could never access it. We would know with certainty that our universe is not all that exists, that we are embedded in something greater. This might provide a sense of context and connection, a feeling that we are part of a cosmic hierarchy rather than isolated in a single, perhaps unique, cosmos. On the other hand, knowing that we are trapped behind an event horizon, forever cut off from any larger reality, might induce a kind of cosmic claustrophobia. The universe is already almost incomprehensibly vast from our human perspective. The observable universe extends some 46 billion light-years in every direction, containing perhaps 2 trillion galaxies. Even traveling at the speed of light, which is physically impossible for material objects, it would take billions of years to cross even a small fraction of this volume. Adding an event horizon boundary to this already enormous space might seem redundant, an additional constraint that makes no practical difference. But psychologically, knowing that there is an absolute boundary, a fundamental limit beyond which no future technology could ever take us, might feel limiting in a way that an infinite universe, however practically inaccessible, does not. These psychological and philosophical reactions would likely vary greatly among individuals and cultures. Some might find the idea disturbing, a cause for existential anxiety. Others might find it liberating, a reminder that our significance does not depend on the size or structure of the universe, but on what we make of our existence within whatever context we find ourselves. Still others might see it as irrelevant, a purely abstract question with no bearing on the practical and moral questions that actually matter in human life. Consider also how the hypothesis might fail and what we would learn from its failure. Suppose that over the coming years and decades, astronomers gather more data on galaxy rotations and find that the initial pattern does not hold up. Perhaps with a larger sample, the preference for one rotation direction disappears, revealed as a statistical fluctuation in a small dataset. Perhaps more careful analysis shows that the pattern is an artifact of observational bias or measurement error. Or perhaps the pattern is real, but is explained by some conventional astrophysical process, such as large-scale velocity flows in the early universe or the influence of primordial magnetic fields. In any of these cases, the black hole hypothesis would lose its primary observational motivation and would likely fade from serious consideration. But even in this case, science would gain something valuable. The investigation would have prompted astronomers to measure galaxy rotations more carefully, to develop better statistical methods for detecting large-scale patterns, to think more deeply about observational biases and systematic errors. It would have motivated theorists to explore alternative cosmological models, to work out the detailed predictions of black hole universe scenarios, to develop new mathematical tools for analyzing curved spacetime geometries. These tools and insights would remain useful even if the specific hypothesis that motivated them turned out to be wrong. This is how science often progresses. A bold idea, even if ultimately incorrect, can stimulate research that leads to other discoveries and deepens our understanding in unexpected ways. The history of cosmology is filled with such examples. The steady-state theory, which proposed that the universe had no beginning but maintained a constant density as it expanded through the continuous creation of new matter, turned out to be wrong. But the debate between steady-state and Big Bang cosmology in the mid-20th century spurred crucial observations, including the discovery of the cosmic microwave background, which definitively ruled out the steady-state model and provided strong evidence for the Big Bang. The steady-state theory failed, but the scientific effort to test it succeeded in advancing our knowledge enormously. Similarly, inflation, the idea that the very early universe underwent a brief period of exponential expansion, was proposed in the 1980s to solve several problems with the standard Big Bang model. Inflation predicts that the universe should be flat, meaning its large-scale geometry is Euclidean rather than curved, and that the density fluctuations seen in the cosmic microwave background should have particular statistical properties. Observations have confirmed these predictions with remarkable precision, making inflation the leading theory for the early universe. But inflation itself raises new questions. What caused it? What is the inflaton field that drove the expansion? Did inflation happen once, or is it an eternal process generating an infinite multiverse? These questions remain unanswered, and future observations might show that inflation, despite its successes, is not the complete story. The black hole universe hypothesis fits into this broader pattern of scientific speculation and testing. It addresses real puzzles, such as the apparent fine-tuning of cosmic parameters, and now, potentially, the alignment of galaxy rotations. By proposing a novel framework that changes our basic picture of what the universe is. If it succeeds, if observations continue to support it, and no alternative explanation proves more compelling, it would represent a revolution in cosmology comparable to the shift from geocentrism to heliocentrism, or from a static universe to an expanding one. If it fails, it will still have served the purpose of pushing us to look more carefully at our observations, to question our assumptions, and to develop our theoretical tools. What can future telescopes and observations do to test these ideas more rigorously? The JWST, remarkable as it is, represents just one platform among many in a growing arsenal of astronomical instruments. On the ground, massive telescopes like the extremely large telescope currently under construction in Chile will have mirrors over 30 meters in diameter, compared to JWST's 6.5 meters. These enormous light-gathering surfaces will allow astronomers to observe fainter and more distant objects with greater detail than ever before. They will be able to measure the properties of individual stars in distant galaxies, to study the chemical composition of early stellar populations, to track the motions of gas and stars within galaxies with unprecedented precision. In space, future missions are already being planned that will complement and extend JWST's capabilities. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will have a field of view 100 times larger than JWST's, allowing it to survey vast areas of sky quickly. This will enable studies of cosmic structure on the largest scales, potentially revealing patterns and correlations that are invisible in smaller surveys. The European Space Agency's Euclid mission, already launched, is designed to map the large-scale structure of the universe and probe the nature of dark energy and dark matter through precise measurements of galaxy shapes and positions. These shape measurements are sensitive to the weak gravitational lensing caused by intervening matter, providing a three-dimensional map of how mass is distributed throughout the universe. Even more ambitious concepts are being discussed for the decades beyond. A space telescope with a mirror 50 or even 100 meters across would be able to image Earth-like planets orbiting nearby stars, potentially detecting signs of life in their atmospheres. Such an instrument would also revolutionize cosmology, allowing us to observe the very first generation of stars that formed in the universe, to measure the properties of the earliest black holes and galaxies, to probe cosmic structure at scales and epochs currently beyond our reach. Building such a telescope would require new technologies for constructing and deploying large structures in space. But it is not physically impossible, merely extremely challenging and expensive. Gravitational wave astronomy represents another frontier that could shed light on fundamental cosmology. Since the first detection of gravitational waves in 2015, observatories like LIGO and Virgo have detected dozens of mergers between black holes and neutron stars, opening an entirely new window on the universe. These waves carry information about the most violent and energetic events in the cosmos, events that are often invisible or barely visible to conventional telescopes. Future gravitational wave detectors, both ground-based and space-based, will be far more sensitive and will observe waves across a broader range of frequencies. The planned LISA mission, a space-based detector consisting of 3 spacecraft flying in formation millions of kilometers apart, will detect low-frequency gravitational waves from supermassive black hole mergers, from compact binary stars in our galaxy, and possibly from exotic sources in the early universe. Gravitational waves from the Big Bang itself, if they exist at detectable levels, would encode information about the very first instance of cosmic history, potentially including the period of inflation. Detecting these primordial gravitational waves would be one of the greatest achievements in physics, providing direct evidence about conditions at energy scales far beyond anything we can recreate in particle accelerators. The properties of these waves might also reveal whether the universe has the unusual topology or geometry expected in a black hole universe scenario, though working out the specific predictions and determining how to test them remains a theoretical challenge. Advances in particle physics could also contribute to understanding these questions. The Large Hadron Collider, the world's most powerful particle accelerator, has been exploring the fundamental constituents of matter and the forces that govern them. The discovery of the Higgs boson in 2012 completed the standard model of particle physics, but many questions remain unanswered. What is dark matter made of? Why is there more matter than antimatter in the universe? Are there additional dimensions of space beyond the three we experience? Do the forces of nature unify at extremely high energies into a single, more fundamental force? Future particle accelerators, whether more powerful versions of current designs or entirely new approaches, might answer some of these questions, and in doing so, shed light on the conditions in the very early universe. The intersection of quantum mechanics and gravity represents perhaps the deepest challenge in fundamental physics. General relativity, our best theory of gravity, describes spacetime as a smooth, continuous fabric that can be curved by matter and energy. Quantum mechanics, our best theory of the very small, describes reality as fundamentally discrete and probabilistic, with particles and fields existing in superpositions of states until measured. These two frameworks have been extraordinarily successful in their respective domains, but they are mutually incompatible in their current forms. Attempts to apply quantum mechanics to gravity lead to mathematical inconsistencies, infinities that cannot be removed by standard techniques. Understanding gravity at the quantum level is essential for describing situations where both gravity and quantum effects are important. The interiors of black holes, the moment of the Big Bang, and potentially the overall structure of space-time itself. String theory, loop quantum gravity, and other approaches to quantum gravity each offer different perspectives on how to reconcile these frameworks. String theory proposes that the fundamental constituents of reality are not point particles, but tiny vibrating strings, with different vibration modes corresponding to different particles. This framework naturally includes gravity and has the mathematical richness to potentially describe all forces and particles in a unified way. Loop quantum gravity, by contrast, maintains that space-time itself is quantized, made of discrete chunks or loops at the smallest scales, avoiding the infinities that plague other approaches. Each of these theories makes predictions about extreme conditions, about the structure of black hole interiors, about the earliest moments of the universe. If we could test these predictions observationally, we would gain crucial insight into which approach is correct and what quantum gravity tells us about the nature of reality. The black hole universe hypothesis exists in this context of fundamental uncertainty about the quantum nature of gravity and space-time. If we cannot fully describe what happens inside a black hole, how can we evaluate whether the universe might be such an interior? The hypothesis is necessarily speculative, pushing beyond the boundaries of established theory into territory where we lack both comprehensive theoretical frameworks and direct observational tests. Yet, it is precisely in such territory that breakthroughs often occur. Physics advances not just by incremental refinement of existing theories, but by bold leaps that reframe entire questions, that reveal assumptions we did not know we were making, that open new ways of thinking about old problems. Consider the notion of scientific paradigms, introduced by philosopher Thomas Kuhn in his influential book, The Structure of Scientific Revolutions. Kuhn argued that science does not progress smoothly and continuously, but rather through periods of normal science, where researchers work within an established framework, punctuated by revolutionary shifts where the entire framework changes. During normal science, anomalies accumulate, observations that do not quite fit the prevailing theory, but are not severe enough to overturn it. Scientists develop ad hoc explanations for these anomalies, or simply set them aside as puzzles to be solved later. But if the anomalies become too numerous or too significant, confidence in the paradigm erodes. Eventually, a new paradigm emerges, one that explains the anomalies naturally while also accounting for most or all of the successors of the old paradigm. This shift, this scientific revolution, transforms how scientists think about their subject, what questions they ask, what methods they use, even what counts as an acceptable explanation. The shift from Newtonian mechanics to relativity exemplifies this pattern. For 2 centuries, Newton's laws of motion and gravity reigned supreme, explaining everything from falling apples to planetary orbits with extraordinary accuracy. But by the late 19th century, small anomalies had accumulated. The orbit of Mercury showed a slight precession that Newtonian gravity could not fully explain. The speed of light appeared to be the same for all observers regardless of their motion, contradicting the Newtonian assumption that velocities simply add. Attempts to detect Earth's motion through the hypothetical medium that carried light waves, the luminiferous ether, consistently failed. These anomalies prompted Einstein to develop special relativity in 1905 and general relativity in 1915, theories that fundamentally reconceived space, time, and gravity. In the new paradigm, space and time were not separate absolutes, but were woven together into a 4-dimensional spacetime that could be curved by matter and energy. Gravity was not a force acting across space, but a manifestation of spacetime curvature. Are we on the verge of another such paradigm shift in cosmology? The alignment of galaxy rotations, if confirmed and unexplained by conventional physics, could be the kind of anomaly that signals the need for a new framework. The black hole universe hypothesis is one candidate for that new framework, though certainly not the only one. Other ideas include modifications to general relativity on cosmic scales, the influence of extra-spatial dimensions, effects from quantum gravity becoming important at large scales, or even the possibility that the cosmological principle is simply wrong and the universe is not homogeneous and isotropic. Determining which, if any, of these ideas is correct will require years or decades of careful observation, rigorous analysis, and creative theorizing. Throughout this process, it is crucial to maintain what might be called intellectual humility, a recognition that our current understanding, however impressive, is almost certainly incomplete and possibly wrong in significant ways. Every generation of scientists has believed they were close to a complete understanding of the universe, and every generation has been humbled by subsequent discoveries. In the late 19th century, physicists believed that the fundamental laws were essentially complete, with only a few minor details left to work out. Those minor details turned out to be the gateways to quantum mechanics and relativity, which revolutionized physics. In the mid-20th century, the success of the Standard Model of particle physics and the Big Bang model of cosmology suggested that we were approaching a final theory. Yet dark matter, dark energy, the hierarchy problem, the strong CP problem, and numerous other puzzles indicate that we are still missing major pieces of the story. This history should make us cautious about dismissing radical ideas too quickly. The black hole universe hypothesis may seem outlandish, but so did many ideas that are now accepted as fundamental truths. The notion that Earth moves through space at tremendous velocity seemed absurd to many in the 16th century, contradicting everyday experience. The idea that matter is mostly empty space, with atoms being tiny nuclei, surrounded by even tinier electrons, separated by vast distances at atomic scales, seemed bizarre when first proposed. The claim that space and time are relative, that simultaneity is not absolute, that objects contract and time dilates depending on motion, struck many as philosophical nonsense when Einstein first presented it. Even the Big Bang itself, now the cornerstone of cosmology, was initially treated with skepticism and even mockery, with some astronomers preferring the steady-state alternative precisely because it did not require a beginning to the universe, which seemed philosophically problematic. What distinguishes scientific speculation from mere fantasy is not conservatism or a refusal to consider radical possibilities, but rather a commitment to grounding ideas in observation and mathematics, to making testable predictions, to accepting the verdict of evidence even when it contradicts our expectations or preferences. The black hole universe hypothesis, speculative though it is, can be evaluated by these criteria. It attempts to explain specific observations, such as the galaxy rotation alignment, within the framework of established physics, general relativity. It makes predictions, or at least suggests observational signatures, that could in principle be tested with better data or more sophisticated analysis. It is expressed in mathematical language that allows for precise calculation and comparison with alternatives. These features make it a legitimate scientific hypothesis, worthy of investigation, even if it ultimately proves incorrect. As we contemplate the possibility that we might be living inside a black hole, it is worth reflecting on what such a discovery would mean for humanity's self-understanding and our sense of cosmic significance. For much of human history, people believed they occupied a special place in the cosmos. The Earth was the center. The heavens revolved around us. Humanity was the pinnacle of creation. This geocentric, anthropocentric worldview provided a comforting sense of importance and purpose. We mattered. Our world mattered. The cosmos was arranged for our benefit, or at least with our existence in mind. The scientific revolution systematically dismantled this view. Earth is not the center, but one planet among many orbiting an ordinary star. The Sun is one star among hundreds of billions in a galaxy that is itself one among hundreds of billions. We occupy no privileged position in space. We exist at no special time in cosmic history. The laws of physics are the same everywhere, make no reference to human existence, and operated for billions of years before we appeared and will continue operating long after we are gone. This Copernican revolution in thought, this displacement from the center, has been one of the great themes of modern intellectual history. Learning that we are inside a black hole would be another step in this progression, perhaps a final one. Not only are we not at the center, not only are we insignificant at cosmic scales, but the entire observable universe, everything we have ever seen or could ever see, is itself bounded, enclosed structure, one black hole among perhaps infinitely many. Our cosmic significance shrinks even further. We are not just small within the universe. The universe itself is small, is contained, is limited in a way we never imagined. Yet, there is another way to view this situation, one that restores a different kind of significance. If we can figure this out, if human beings with our brief lifespans and tiny brains can discover that the universe is a black hole interior, if we can understand the mathematical structure of spacetime well enough to recognize the truth of our cosmic situation, then in that very achievement, we demonstrate something profound about consciousness and intelligence. We would have succeeded in understanding the container that holds us, in seeing beyond the immediate appearances to the deeper reality. This capacity for understanding, for abstract thought, for mathematics and logic and observation, would stand as something truly remarkable in the cosmos. Perhaps the most remarkable thing of all. The drive to understand, the curiosity that leads us to build telescopes and particle accelerators and develop theories of quantum gravity. This impulse seems to be fundamental to human nature. We want to know where we came from, what we are made of, how the universe works, what our place in it is. These questions have motivated scientists and philosophers for millennia, and they continue to motivate research at the frontiers of knowledge today. The black hole universe hypothesis, whether right or wrong, emerges from this deep human need to understand. It represents our species reaching out with our minds toward the largest questions we can conceive, questions about the nature and structure of reality itself. In the end, the most honest answer we can give to the question of whether we are inside a black hole is that we do not know. The observations that inspired the hypothesis are suggestive, but not conclusive. The theoretical framework exists to describe such a scenario, but lacks the detailed development and testing needed to be considered established science. Future observations may strengthen the case, or they may reveal that the apparent anomalies have mundane explanations. The scientific process will continue, with observations and theory engaging in dialogue, each informing and constraining the other, gradually converging on something closer to truth. What we can say with confidence is that the universe continues to surprise us, to reveal complexities and mysteries that our current theories do not fully capture. The James Webb Space Telescope, peering into the ancient past, has already shown us galaxies that are brighter, more massive, and more structured than we expected at such early times. It has revealed exquisite details of planetary atmospheres, of star formation regions, of the deaths of massive stars. And now, potentially, it has revealed a pattern in galactic rotations that challenges our assumption of cosmic randomness. Whether this pattern points toward a black hole universe, toward modified gravity, toward topological effects, or toward something we have not yet imagined, it reminds us that our understanding remains incomplete. The story of the universe is still being written, both by the cosmos itself as it evolves through time, and by scientists working to understand that evolution. We stand at a particular moment in this dual story, equipped with unprecedented observational tools and sophisticated theoretical frameworks, yet still confronting deep mysteries. The possibility that we are inside a black hole is just one of many questions at the frontiers of cosmology. What is dark matter? What is dark energy? Did inflation occur? Are there other universes? What came before the Big Bang? Is time fundamental or emergent? Are space and dimensionality fundamental or emergent? Each of these questions pushes against the boundaries of our knowledge, and answering them will require breakthroughs in observation, theory, and perhaps in ways of thinking that we have not yet developed. The universe, whether a black hole interior or something else entirely, is far more mysterious and wonderful than we can fully grasp. This is not a cause for despair, but for excitement and engagement. Every answer we find opens new questions. Every mystery we solve reveals deeper mysteries beneath. The journey of understanding has no final destination, no point at which we can say we know everything and there is nothing left to discover. There will always be another horizon to reach toward, another puzzle to investigate, another aspect of reality to illuminate with the light of human reason and observation. And that, perhaps, is the real story. Not whether we are trapped in a black hole, but that we are capable of asking the question, of seeking the answer, of reaching beyond ourselves toward an understanding of the cosmos that contains us. In that reaching, in that eternal striving to know, we find our deepest purpose and our truest significance, whatever the ultimate structure of reality may turn out to be. The investigation into whether our universe might be contained within a black hole requires us to delve deeper into the mathematical foundations of cosmology and the specific ways in which black hole physics differs from our standard models of cosmic evolution. When cosmologists calculate the properties of the universe, they begin with Einstein's field equations, the fundamental relationships of general relativity that connect the curvature of spacetime to the distribution of matter and energy. These equations are notoriously difficult to solve in their full generality, containing 10 coupled, nonlinear partial differential equations that must be satisfied simultaneously. To make progress, cosmologists invoke symmetries that simplify the mathematics while still capturing the essential physics. The most important of these symmetries is the assumption of homogeneity and isotropy embodied in the cosmological principle. This assumption allows cosmologists to use the Friedmann-Lemaitre-Robertson-Walker metric, a mathematical description of spacetime that is the same at every point and the same in every direction. With this metric, Einstein's field equations reduce to two much simpler equations called the Friedmann equations, which describe how the scale factor of the universe, essentially the size of the universe at any given time, evolves based on its energy content. These equations have been solved for various combinations of matter, radiation, and dark energy, producing predictions that match observations remarkably well. The universe appears to have gone through several distinct phases. An early radiation-dominated era when photons and other relativistic particles controlled the expansion. A later matter-dominated era when galaxies and dark matter became the dominant influence. And finally, the current dark energy-dominated era when the expansion is accelerating. But inside a black hole, the situation is fundamentally different. The Schwarzschild metric, which describes the simplest type of black hole with mass but no charge or rotation, divides spacetime into an exterior region and an interior region separated by the event horizon. In the exterior region, outside the horizon, space and time behave in ways that are unusual but comprehensible. Clocks run slower closer to the black hole due to gravitational time dilation, and space is curved so that trajectories bend toward the center. But the basic character of space and time remains intact. Space is space, time is time, and you can move through space while being carried forward through time. Inside the horizon, this character fundamentally changes. In a sense that can be made mathematically precise, the roles of space and time switch. The radial coordinate, the distance from the center, becomes time-like, meaning it has properties similar to time in the exterior region. You are inevitably carried toward smaller radial values, toward the singularity at the center, just as you are inevitably carried toward the future in normal space-time. There is no way to stop or reverse this motion, no amount of acceleration or maneuvering that can prevent you from reaching the singularity. Meanwhile, the time coordinate becomes space-like, having properties more like space. This mathematical role reversal represents the most alien feature of black hole interiors, a complete transformation of the structure of reality compared to the universe we experience outside. For a rotating black hole described by the Kerr metric, the interior structure becomes even more complex. The singularity is no longer a point, but a ring, and the space-time develops additional regions with properties that challenge our physical intuition. Frame dragging becomes extreme, forcing everything to rotate in the direction of the black hole's spin. There are closed time-like curves, paths through space-time that loop back on themselves, potentially allowing travel to the past. Whether such features are physically real or mathematical artifacts that would be eliminated in a complete theory of quantum gravity remains debated, but they indicate just how strange black hole interiors can be. Now, Imagine trying to map the evolution of an entire universe onto the interior of such a structure. The challenge is to find a solution to Einstein's equations that has the character of a black hole from some external perspective, but looks like an expanding universe from the interior perspective. Such solutions do exist in the mathematical literature. Some of the earliest were explored in the 1960s and 1970s, when physicists first began seriously investigating the implications of general relativity for cosmology. One class of solutions involves what are called Einstein-Rosen bridges, sometimes known as wormholes, where a black hole in one universe connects to a white hole in another, with the connecting throat potentially serving as an interior universe. More recently, some theorists have explored the idea that the Big Bang itself might be understood as a kind of black hole formation event. In these models, what we call the Big Bang is not a singularity in the conventional sense, but rather a transition or bounce, a moment when a previous contracting phase reversed into our current expanding phase. The mathematics of such models often involves modifications to general relativity that incorporate quantum effects, allowing the equations to remain well-behaved even at extremely high densities where classical general relativity predicts a singularity. If the universe is the interior of a black hole, the Big Bang might represent the initial formation of that black hole as seen from inside, with the subsequent expansion being the natural evolution of the interior volume. These theoretical models are mathematically consistent, meaning they do not violate the fundamental principles of general relativity, but they face significant challenges in matching all of our detailed observations. The cosmic microwave background, for instance, provides exquisitely precise information about conditions in the early universe. The temperature fluctuations in the CMB have been measured to a precision of better than 1 part in a million, and their statistical properties depend sensitively on the composition and evolution of the early universe. Any black hole universe model must reproduce these observations, and doing so requires careful tuning of parameters and initial conditions. So far, no black hole cosmology has been developed that matches observations as well as the standard lambda CDM model, while also making novel predictions that can distinguish it clearly from the standard model. The challenge is not merely technical but conceptual. If we are inside a black hole, what does that even mean for our observations? An event horizon is defined relative to infinity in spacetime, relative to a distant external region that serves as a reference point. But if we are inside, we have no access to that external region, no way to know where the horizon is, or even whether it exists in the form we imagine. The interior might be finite in spatial extent, but still appear infinite to observers within it, just as the surface of a sphere is finite but unbounded, having no edge or boundary that an inhabitant of the surface can reach. Alternatively, the interior might truly be infinite in spatial extent, with the black hole structure imposing constraints on the topology or curvature rather than on the total volume. These ambiguities reflect deeper questions about what it means to test a theory that makes claims about regions of spacetime that are fundamentally inaccessible. In conventional science, we test theories by making predictions about observable quantities and checking those predictions against measurements. But if a theory predicts something about a region beyond our cosmic horizon, a region we cannot observe even in principle, has it made a scientific prediction at all? This is not merely a philosophical quibble, but a practical problem that physicists face when working on theories of quantum gravity, string theory, and cosmology. One approach to this problem is to focus on observable consequences that arise from the unobservable features. Even if we cannot see beyond our horizon, the existence and properties of that horizon might affect things we can observe. In the case of a black hole universe, the topology and global geometry could produce observable effects through subtle correlations in the cosmic microwave background, through gravitational lensing patterns, or through features like the alignment of galaxy rotations. These would be indirect signatures, hints about the global structure inferred from local measurements, but they would still be testable predictions that distinguish the black hole universe hypothesis from alternatives. Another approach involves examining the internal consistency and logical coherence of the theory. Even if we cannot directly test all aspects of a theory, we can ask whether it hangs together, whether it makes sense as a complete picture, whether it naturally explains features that seem arbitrary or coincidental in other frameworks. String theory, for example, makes predictions about physics at energies far beyond what we can ever reach with particle accelerators, at the Planck scale where quantum gravity effects become dominant. We cannot directly test those predictions, but we can test whether string theory makes sense as a mathematical structure, whether it reduces to known physics at lower energies, whether it provides insights into problems like black hole thermodynamics that other approaches struggle with. If it succeeds on these fronts, that provides indirect support even without direct observational tests of its most exotic predictions. The black hole universe hypothesis could be evaluated similarly. Does it provide a natural explanation for features of the universe that seem fine-tuned or arbitrary in standard cosmology? Does it resolve paradoxes or tensions in our current understanding? Does it make contact with other areas of physics in interesting ways? If the hypothesis succeeds on these criteria, it gains credibility, even if some of its specific claims remain difficult or impossible to test directly. Consider again the fine-tuning problems that have long puzzled cosmologists. The flatness problem asks why the universe is so close to the critical density that separates eternal expansion from eventual recollapse. Calculations show that for the universe to be as flat as we observe today, it must have been incredibly flat in the early universe, with the density parameter differing from 1 by less than 1 part in 10 to the 60th. This seems like an extraordinary coincidence, unless something in the early universe drove the geometry toward flatness. Inflation solves this problem by exponentially expanding the universe, smoothing out any initial curvature and driving the geometry toward flatness regardless of initial conditions. But if the universe is a black hole interior, perhaps flatness is not a coincidence or the result of inflation, but simply a property of the black hole geometry itself. The interior of a sufficiently massive black hole can appear very flat to observers within it, just as the surface of a very large sphere appears flat to small creatures living on that surface. The observed flatness would then reflect the size and mass of the black hole, rather than special initial conditions or an inflationary phase. This does not eliminate the need for inflation entirely, because inflation solves other problems as well, but it suggests that some of the apparent fine-tuning might have a geometric rather than dynamical explanation. Similarly, the cosmological constant problem asks why the dark energy density is so small compared to naive theoretical expectations, yet not exactly zero. Quantum field theory predicts that empty space should have an enormous energy density due to quantum fluctuations, some 120 orders of magnitude larger than the observed dark energy density. This is perhaps the worst prediction in all of physics, a discrepancy so vast that it suggests we are missing something fundamental about how quantum mechanics and gravity interact. Various solutions have been proposed, including anthropic arguments that only universes with small, Cosmological constants can support life and therefore observers, but none has gained universal acceptance. In a black hole universe, the cosmological constant might be related to the black hole's properties in ways that constrain its value. Some models suggest that the apparent acceleration of cosmic expansion is not due to dark energy at all, but is a consequence of the interior geometry of the black hole, a misinterpretation of how distances and velocities work within such a structure. If this were true, it would eliminate the need for dark energy altogether, though it would still require explaining why the interior geometry produces effects that mimic a small positive cosmological constant so precisely. Other models retain dark energy, but suggest its value is set by boundary conditions at the black hole horizon, providing a mechanism that could naturally produce a small but non-zero value. These are tantalizing possibilities, but they remain speculative. No complete and detailed black hole cosmology exists that resolves these fine-tuning problems while also matching all observations. The hypothesis is suggestive, pointing toward connections and explanations that might exist. But the hard work of developing those connections into a full theory remains to be done. This is typical of radical ideas in physics. They begin as vague intuitions or bold speculations, and only through years or decades of effort do they mature into precise, testable theories. Many such ideas fail along the way, unable to overcome technical obstacles or contradicted by new observations. A few succeed, transforming our understanding and opening new frontiers for exploration. The process by which science evaluates and ultimately accepts or rejects such ideas is fascinating in itself. Scientific knowledge is sometimes portrayed as a collection of facts, as a body of established truths that students must memorize and accept. But at the research frontier, science is far more dynamic and uncertain. It is a conversation, an ongoing debate among researchers who bring different perspectives, different techniques, different priorities. Some scientists are conservative, preferring to work within established frameworks and extending them incrementally. Others are more radical, willing to challenge fundamental assumptions and explore unconventional ideas. Both types are necessary for healthy progress. The conservative researchers serve as gatekeepers, ensuring that new ideas meet high standards of rigor and evidence before being accepted. They ask hard questions. What exactly does this theory predict? How do we test it? What could prove it wrong? They insist on clarity and precision, on mathematical details worked out fully, on all objections addressed. This skepticism prevents science from fragmenting into competing schools based on personal preference or philosophical taste rather than empirical evidence. It maintains the connection between theory and observation that makes science uniquely successful at producing reliable knowledge about the natural world. The radical researchers serve as explorers, venturing into new territory and proposing ideas that conservatives might initially reject as too speculative or poorly defined. They ask different questions. What if we are thinking about this wrong? What assumptions are we making? Unconsciously, what entirely different approach might work? They are willing to work with incomplete theories, to follow mathematical hints even when the physical interpretation is unclear, to entertain possibilities that seem bizarre or counterintuitive. This willingness to explore beyond established boundaries is essential for breakthroughs, for escaping conceptual traps, for discovering the truly new, rather than merely elaborating the known. The tension between these approaches is creative and productive when it functions well. The radicals propose bold ideas, and the conservatives subject those ideas to rigorous scrutiny. Ideas that survive this scrutiny gain credibility and attract more attention and effort. Those that fail are set aside, though sometimes they are revisited later when new insights or techniques make them more viable. Through this process of proposal, criticism, testing, and revision, science gradually converges on better theories, more accurate descriptions of reality. The black hole universe hypothesis is currently in the early stages of this process. A few researchers are developing the idea, working out its implications, identifying potential tests. A larger group is watching with interest but maintaining skepticism, waiting to see whether the hypothesis can overcome its challenges and produce clear predictions. The majority of cosmologists are focused on other questions entirely, working on problems where the path forward is clearer and the chances of making progress are higher. This distribution of effort is reasonable and natural. Science cannot afford to have everyone chase speculative ideas. Most researchers must work on incremental problems that gradually build the foundation of knowledge. But science also cannot afford to have no one chase speculative ideas. Breakthroughs require someone to venture beyond the safe and established. As observers of this process, whether as scientists ourselves or as interested members of the public, we should resist the temptation to demand premature certainty. It is perfectly acceptable for scientists to say, "We don't know," or "The evidence is unclear," or "There are several competing hypotheses and we haven't determined which is correct." These are not signs of failure, but signs of honest engagement with genuinely difficult questions. The universe does not owe us easy answers, and our current theories, successful as they are, almost certainly do not capture the complete truth. This honest acknowledgement of uncertainty is particularly important when communicating science to broader audiences. Popular science writing and documentaries sometimes present scientific ideas with more confidence than is warranted, eliding caveats and uncertainties in the pursuit of a compelling narrative. A documentary might say, "Scientists have discovered that the universe is inside a black hole," when what scientists have actually done is observed a pattern that might be explained if the universe is inside a black hole, though other explanations are possible and more data is needed. The first phrasing is more dramatic and attention-grabbing, but it misleads people about how science actually works and sets up false expectations about the reliability of scientific claims. The reality is that frontier science is messy and uncertain, full of competing ideas and incomplete theories and ambiguous observations. This is not a bug, but a feature, a sign that we are working at the edge of human knowledge where real discoveries become possible. The process of sorting through this mess, of gradually clarifying which ideas work and which don't, is precisely what makes science powerful. It is a collective enterprise, with thousands of researchers contributing different pieces, with mistakes made and corrected, with dead ends explored and abandoned, with unexpected connections discovered and exploited. The outcome is not perfect certainty, but progressively more accurate and comprehensive understanding. In the specific case of the galaxy rotation alignment, the scientific process is just beginning. The initial observation has been reported and is attracting attention. Other research groups will attempt to replicate the finding using independent data sets. Theorists will work on developing more precise predictions for what a black hole universe should look like and how to distinguish it from alternatives. Observers will design new surveys specifically targeted at measuring galaxy rotations more accurately and for larger samples. This will take time, likely years or decades, and the outcome is genuinely uncertain. It is possible that the alignment will prove to be real and robust, surviving all attempts to explain it away, and that the black hole hypothesis, or something like it, will emerge as the best explanation. In that case, we would witness a genuine revolution in cosmology, a fundamental reconceptualization of what the universe is. Textbooks would be rewritten, new research programs would launch, and our cosmic story would change profoundly. Future generations would look back on this discovery as a turning point comparable to the Copernican revolution or the discovery of cosmic expansion. It is equally possible that the alignment will prove to be a statistical fluke or an artifact of observational bias, disappearing when better data are collected. This would not represent a failure of science, but simply the normal process by which apparent anomalies are investigated and resolved. We would learn something about the systematic errors in galaxy rotation measurements, something about the statistical techniques needed to detect genuine large-scale patterns, something about how to avoid being fooled by random fluctuations in small datasets. This knowledge would be valuable for future research, even though the specific anomaly that motivated it turned out to be illusory. A third possibility is that the alignment is real, but has a more conventional explanation than a black hole universe. Perhaps it reflects previously unknown physics of galaxy formation, or the influence of large-scale magnetic fields, or some subtle effect of the cosmic web of matter that connects all galaxies. Determining the correct explanation would advance our understanding of cosmic structure and might open new avenues for research. The black hole hypothesis would fade into the background, an interesting idea that didn't pan out, but that served a useful purpose by motivating research that led to the actual explanation. Regardless of which path this investigation ultimately follows, the journey itself has value. The questions raised about the nature of the universe, the structure of spacetime, the reliability of our observations, these are profound questions worthy of serious attention. Engaging with them deepens our understanding, even when we don't immediately reach definitive answers. It exercises our capacity for abstract thought, for mathematical reasoning, for careful observation and analysis. It reminds us of how much we have learned about the cosmos and how much remains to be discovered. For those of us who are not professional cosmologists, following this story offers a window into how science operates at its frontiers. We can see the initial excitement over a surprising observation, the careful scrutiny that follows, the proposal of multiple explanations, the design of tests to distinguish among them. We can appreciate both the ambition of trying to understand the largest scales of reality and the humility required to acknowledge how much remains uncertain. We can recognize that science is not a collection of facts handed down by authorities, but an ongoing human endeavor, flawed and fallible, but self-correcting, driven by curiosity and constrained by evidence. The question of whether we are inside a black hole ultimately connects to the deepest questions humans have asked about existence. What is real? How do we know what we know? What is our place in the cosmos? These are ancient questions, asked by philosophers and theologians and mystics throughout human history. Science offers a distinctive approach to these questions, grounded in observation and mathematics, rather than revelation or pure reason. But the questions themselves transcend any single discipline or method. They speak to something fundamental in human consciousness, a drive to understand that seems intrinsic to our nature. Perhaps this drive is what gives our existence meaning, regardless of whether we are in a black hole universe or a conventional expanding universe or something else entirely. The structure of the cosmos, vast and complex as it is, provides the stage for our existence, but the meaning we find comes not from the stage, but from what we do on it. We build, we create, we love, we think, we question, we explore. These activities matter to us not because of where we are in the cosmic hierarchy, but because of what they mean for our experience, for our relationships, for our sense of purpose and accomplishment. Yet there is also something ennobling about reaching beyond our immediate concerns to contemplate the largest questions we can conceive. When we look up at the night sky and wonder about the nature of the universe, when we build telescopes to peer billions of years into the past, when we develop mathematical theories to describe the curvature of spacetime, we are transcending the merely local and immediate. We are participating in something larger than ourselves, a collective human project of understanding that spans generations and cultures. We are demonstrating that consciousness, that remarkable property of certain configurations of matter that allows them to become aware and to think, can reach out from a small planet to comprehend structures on the largest imaginable scales. This capacity for cosmic understanding is perhaps the most remarkable feature of our existence. We are, as Carl Sagan famously noted, a way for the cosmos to know itself. We are arrangements of atoms, forged in the cores of dying stars, assembled by the blind processes of chemistry and evolution, somehow giving rise to subjective experience and rational thought. And with that thought, we can understand the very processes that created us, can trace our origins back to the Big Bang, can project our future forward to the end of the universe. We can even ask whether the universe itself is contained within a black hole, whether there are levels of reality beyond what we can observe. The fact that these questions arise, that we can formulate them precisely and seek answers through observation and reasoning, is itself a kind of answer to the question of our cosmic significance. So, as we await further observations from JWST and other telescopes, as theorists continue to work on models of black hole cosmology and alternatives, as the scientific process gradually converges on better understanding, we can appreciate the journey itself. We can marvel at what we have learned and remain humble about what we don't know. We can support the research that pushes at the boundaries of knowledge, recognizing that breakthroughs cannot be scheduled or guaranteed, but emerge from sustained effort and occasional flashes of insight. And we can remember that whatever the universe turns out to be, whether a black hole interior or something we haven't yet imagined, the quest to understand it is one of humanity's greatest achievements and most defining characteristics. In that quest, we are most fully ourselves, most fully alive to the mystery and wonder that surrounds us. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.